Okay, welcome back, everybody. Um, so started a little late today. I'm like 10 minutes late, but the lecture will be an hour and 20 minutes long, so we'll stop around 11:30. Okay, so at the end of lecture last time, I had mentioned this fact. I had written it like this. So first of all, we defined the bound degree of a region, which is so remember how we had defined a region of a planar graph. Uh, the bound degree was the number of edges that bound it. So I'll do a quick example of that here again in a second. And then we noticed that for some of those examples that we looked at last time, we noticed this pattern where the number of vertices minus the number of edges plus the number of regions was always 2 for every single one of those examples. So the examples mentioned, like I said, if you don't want to go and look at the last lecture, here were a few of those examples. These are all planar graphs. Let me sharpen it a bit. There we go. Those are all planar graphs. Look, in each case, the number of vertices is n, number of edges is q, the number of regions present is this R. So you might look at this and say, why are there 2 regions? Well, there's an inside and an outside, right? So there's always this outside region. Here, right, why are there 4 regions in this example? Like I explained in last lecture, 1, 2, 3 regions, and then the outside region, for instance. Okay. So, what about bound degree? That's the other thing. So here, let's say here's my example, right? Here's my graph. These are the regions. I explained it as it's kind of like a cookie cutter, where the cookies are the regions you're talking about. So the bound degree of region 1 would be 1, 2, 3, 4, right? The bound degree of region 2 would be 3, because it's bounded by 3 edges. Bound degree of region 5 would also be 3. Bound degree of region 7 would be all of these edges that bound it. Okay, so you have to count those. That's the exterior region. Okay. Now, we notice that in all of those examples, there was this pattern. I'm going to say a lot more about this pattern. I'm actually going to say a lot more about this pattern than the textbook does, because what is going on takes us out of graph theory only slightly, but I think it helps motivate what it is that's happening. Because the very first thing we're going to do with this thing is finally have a tool for showing that a graph is non-planar, right? That's actually the application here. So here is the theorem that solidifies this pattern that we noticed, which is can be called Euler's formula, although Euler's formula can also refer to something else. But in our context, it's clear what we mean. What is Euler's formula? If G is a connected planar graph with n vertices, q edges, and r regions. This R referring to regions is the only reason we don't use a much better way of labeling this, which we are going to use for polyhedra. Then the vertices minus the edges plus the number of regions is always equal to 2. After we have used this a bit, and after I've moved on and talked about polyhedra, I'm going to explain to you what's actually going on here underneath the hood. But for now, you can just say, hey, yeah, I noticed this in all of those examples that I flashed on the screen. So it seems like this is true. Let's see if we can actually prove that this is true. So proof here, I'm going to induct on the number of edges. So we're inducting on Q. Okay. We could start as our base case even Q equals 0. There are no edges, right? If Q is equal to 0, then what is the only connected planar graph with 0 edges? For it to be connected, it's got to be K1, right? G must be the complete graph on a single vertex. Okay, but which has one vertex and one region. Just the exterior region is the only region. Thus, the number of vertices minus the number of edges in this example plus the number of regions is still 2. So the formula is true in our base case with 0 edges, right? So assume the result is true for all connected planar graphs with fewer than Q edges, and assume that G has Q edges. So assume theorem is true for all connected planar graphs with less than Q edges. And suppose the graph G in question has exactly Q edges. Now we want to show that if G has Q edges in vertices in R regions, that this is true, even for G. But right now we're, by the inductive step, we're only assuming that it's true for every graph with less than Q edges. Okay, so it turns out that from here, really the only thing to consider, the only two cases, are whether or not G is a tree. Because our G is connected, of course, this really what this is. Yes, it is still whether or not G is a tree, but since we already know G is connected, this is just saying whether or not G has a cycle. All right, so whether or not G has a cycle is the actual thing that is determining these cases. So case 1, G is a tree, which means it has no cycle. Okay, but since it is a tree, this means that the number of edges is n minus 1. We know G has n vertices, so since it's a tree, the number of edges is n minus 1. Also, since it's a tree, what's the number of regions? Let's go back and look at this quick example. How many regions were present for this tree? 1. You think that's going to be the same for any tree? Yes. Why? A tree doesn't have cycles. A cycle amounts to enclosing a new region that is distinct from the exterior region. You're closing up a region, bounding it off. In a tree, that doesn't happen, so you only get one region. So it's very restricted how this picture looks. And so R is equal to 1 since G is a tree. So n, sorry, I'm gonna have to redo that, plus anyway, so n minus q, but q is n minus 1, plus 1, which is the number of regions here. This is n minus n is 0, minus 1 is 1, plus 1, 1 plus 1 is 2. And the result holds in this case. Case 2, it's not a tree. Well, if it's connected, but it's not a tree, means it has a cycle. So let C be a cycle in G. And let E be an edge of this cycle. Okay, and consider G minus that edge. So consider the graph G, except I have taken away that edge. How do I compare this to G, right? Compared to G, what is the vertex count of G minus E? Remember, when you are deleting an edge from a graph, you don't remove any of the vertices. So I've deleted a single edge, I haven't removed any vertices, so this should have the same number of vertices as G, right? So compared to G, this has the same number of vertices. It has one edge fewer, obviously, because I took away the edge E. And because I took away the edge E was an edge in a cycle. Because it's a cycle, right, and a cycle is a path, taking away that edge necessarily takes away one of the regions. So there was a region, say, like this in the graph. This region, I took away this edge. Now there is no longer this region. I took away this region. This region was closed up by this cycle. But when I remove an edge of a cycle, it's no longer a cycle, which means it doesn't bound a region. Right? And so this has one edge fewer and also one region fewer. This is the key. This is the reason why I did this. It's got one edge fewer and one region fewer. Oh. Well, since it has one edge fewer, that's important because we assumed that this result was true for all connected planar graphs with less than q edges. And here we have something with less than q edges. So the inductive hypothesis applies to this graph that we formed through edge deletion of E, right? So inductive hypothesis applies to G minus E. And so what do we know? We know that for G minus E, it has the same number of vertices. So N minus the number of edges is one less, so this would be Q minus 1. Plus the number of regions is also one less, so this would be R minus 1. We know that this is equal to 2. Okay? This is the inductive hypothesis, that this is equal to 2. I didn't notice anything else and say that this is equal to 2. But if this is equal to 2, simplifying this, this would be minus q minus minus 1, so this is plus 1, plus minus 1, plus 1, minus 1. Those cancel, and this tells me that N minus q plus r is equal to 2, which is what I was trying to show. And we're done. Okay. Now, let's see a result of having this fact in our tool belt. So the immediate application. What is the immediate application of this? Our reasoning for developing this, you might remember, was that, as I explained, to show that a graph is non-planar, what would you need to do? Right? So far, we don't have a single example definitively that we've shown is non-planar. So every single graph we've seen has been a planar graph. But to show that a graph is non-planar, what do we have to do? We would have to show that there could not possibly be a graphical representation that worked, right? That it's just not possible. But that is somehow simultaneously showing that any even conceptual process of doing this is actually impossible. There's not a lot to get your hands on there, so much better would be to come up with a quantity that is invariant in some way, so that for these planar graphs it is always the same. But for a non-planar graph, it might not be. And then you just test the number. So, this isn't the first time you've done something like this in math. The determinant did this. The determinant is a function that took you from a matrix to a real number. And based on the value of that real number, you could say whether a matrix was invertible, right? So if the real number was not 0, it was invertible. If the real number was 0, it was not invertible. That's one example of using a quantity like this. This is another. Actually, it turns out this is a very high-powered example of this, and I'm going to go a little bit into that. But in our case, it's a simple example because we are in the plane. We are dealing with a 2D planar representation of a graph. So that is the reason why this number is particularly simple. But it turns out that this quantity we're computing, that is actually the Euler characteristic, is a very important topological invariant. So I'll talk a little bit about what that means and what it is that's actually going on. So immediate application of this is that that problem we had of the the hyperdogs, megacats, and noble lizard folk. We had them living in a city. They were interested in the 3 places of interest in the city, but we didn't want their paths to cross, so we wanted to come up with a planar representation of K33, this complete bipartite graph size. Both partite sets have size 3. Well, it turns out that is impossible because this is actually non-planar. So, rather than try to cook up some argument that any potential planar representation is impossible without having any tools, we now have the Euler characteristic, which says if this thing was planar, it has to satisfy that formula. So, what do I do? Suppose K33 is planar. And we had some planar representation. You can call it G if you want to. Since K33, I mean, the partite sets each have 3 vertices, so there's a total of 3 plus 3 or 6 vertices. So n is equal to 6. The number of edges we know, it's 9, right? Q is equal to 9. Then Euler's formula, which must apply to a connected, which K33 is, planar graph, which is what we're assuming, Euler's formula applies in this case, and so there must be, if 6 minus 9 plus r is equal to 2, this implies that r must be 5. So there must be 5 regions in this planar representation. Okay. Now you might say, well, what's the problem with that? We have 6 vertices, 9 edges, and 5 regions in our planar representation. That doesn't seem like a problem to me, at least not yet. So now consider the following sum. So I could label this sum C, which is the sum over regions R in the planar representation of the bound number of the region. Maybe I'll write that over here, or the bound degree. This is that number at the beginning of lecture today, which is just the number of edges that bound the region. Okay. Now, of course, every edge of G can be on the boundary of at most 2 regions. So, this is just our definition of bound, right? So it can be on the boundary of at most 2 regions, right? There's on this side and on that side of the edge. That's what's allowed here. So in that case, this sum is less than or equal to just 2 times all of the edges, right? This is like the maximum. If every single edge bounded 2 regions, that's as big as it could ever be. But this Q, we know what that is. It's 9. So this is 18. So this C has to be less than or equal to 18. But also, every region of K33 must be bounded by at least 4 edges. To see why this is, let's see here. Do I actually have a, well, maybe I'll just draw it real quick, right? Let's draw it up here. So we could make the same argument in any bipartite graph, honestly, because you look at this and you might see triangles here, but really there's no triangles here in terms of meeting at vertices, right? Because, for instance, like what is a region, like let's see like what one of these regions would be. Like here's an edge, and then here's an edge, but that doesn't close up a region. To close up a region in this planarity business, what would I do? You might say, well, you need this edge, but again, that doesn't close up a region. and then this edge. Now we finally have enclosed a region. You might look at this and say, no, you've enclosed two regions. No, they don't meet at this vertex. So the point is that for this to be planar, of course, I would have to arrange these in a way that I've moved this picture around so that these don't intersect in this way. But however I did that, right, this would have four edges, four distinct edges that bound it. Okay, and that would be true for any of these regions. You can try this on a smaller bipartite graph. You can try it on any bipartite graph you want to. You're not going to have any triangles like this. You're going to have these quadrilaterals of some type, at least. Okay, and so every region has at least four edges that bound it. So the bound degree is always at least 4, but there's five of these regions. So this implies that C is, whatever it is, it's greater than or equal to 4 times the number of regions, but the number of regions is 5, so this is 20. So this number, this sum over the bound degrees, is less than or equal to 18, but simultaneously greater than or equal to 20. This is impossible. So then what is the only problem here in this entire proof? It was this initial assumption that K through 3 is planar. Thus, K through 3 is not planar. Okay, so this was our tool for showing, there's at least one graph that is non-planar. So that desire we had to solve that problem involving the 3 rival factions in the city, it's actually impossible. There is no planar representation for K through 3. Okay. Next, we have the following theorem that is related to Euler's formula, which is if G is a planar graph with at least 3 vertices and Q edges, then Q is less than or equal to 3n minus 6, and if equality holds, then every region is bounded by 3 edges. So quick proof here. Again, consider the sum over the regions of their bound degrees. So I'm summing the bound degrees here. For the same reason as last time, from last proof, same reasoning, nothing else needs to be assumed. C is always less than or equal to 2 times the number of edges. Okay. Now, since a region is bounded by at least 3 edges and not less, we have the following. So also, since each region is bounded by at least 3 edges, we know that C is greater than or equal to 3 times the number of regions. But C is less than or equal to 2 times the number of edges, 2q. It's greater than or equal to 3r, 3 times the number of regions. This implies that 3 times the number of regions is less than or equal to 2 times the number of edges. Okay. By Euler's formula, though, so Euler's formula applies here, and if n minus q plus r is equal to 2, right, then solving for r here, this means that r is equal to 2 minus n plus q. So in this inequality, this is the same thing as 3 times 2 minus n plus q being less than or equal to 2 times q, which is 6 minus 3n plus 3q is less than or equal to 2q. So I can subtract 2q from both sides. That's a positive number, and I'm subtracting it anyway, so it doesn't matter. So subtracting 2q from both sides leaves me with just a q here, moving everything else over to the right-hand side. This implies that q is less than or equal to 3n minus 6. Okay. If equality holds, then instead of 3r being less than or equal to 2q, 3r is equal to 2q. But then this just means that every region is bounded by 3 edges. So instead of being bounded by at least 3 edges, it's bounded by exactly 3 edges. Okay, because, again, of this relationship to the sum of the bound degree. So that's it. That's exactly the theorem. And I want to use this theorem to prove the next theorem, which is, maybe I should put it on a different page. So, theorem. We mentioned it before, but we didn't actually do anything with it. I just asked a question of whether you could draw a planar representation. But K5 is also non-planar. Okay. Quick proof. Well, I want to use this last theorem that I just proved. This has, well, 5 vertices. And 10 edges. Okay. But then 3n minus 6 is 15 minus 6, which is 9, which is less than 10, which is the number of edges here, q, which is impossible if K5 is planar by the previous theorem. Question in chat, the explanation of why we use the bound degree. The reason why is that basically all of in both cases, so both of the theorems that we used it to prove, we were doing an operation and seeing how it affected the graph. For instance, whether it increased or decreased, removing an edge, whether it increased or decreased, or what it did to the number of regions. The bound degree is useful because it is our way of keeping track of the edges bounding a face, or as we're calling them now, a region. These regions will have a simpler way of thinking about them so the very next thing we're going to do, we're going to see how this applies to regular polyhedra, or just polyhedra in general, how this applies. And in polyhedra, those regions have a much easier to visualize and easier to see thing. And it's clear what the bound degree of every region is because of how polyhedron are defined. Whereas in a graph, it's a little bit messier because you're not, especially for a generic graph that might not be planar, because you're having to deal with a messier object than a polyhedron. So we won't have to worry about bound degree in a polyhedron because it will basically be obvious what the bound degree is. But the reason why we're dealing with the sum, one, it works. We're trying to put a bound on how big that can be or how small it can be, what it has to at least be. And that's what led to the contradiction. So basically, we used it because it worked, more or less. So the equality applying is that in this case, if 3r is equal to 2q, then because c has to be at least 2q, it has to actually be exactly equal to 3r. The reason we got the greater than or equal to 3r case was because every region is bounded by at least 3 edges. But if c is equal to 3r, the only way that can happen is if each region is bounded by exactly 3 edges, which is what we were trying to prove. So that's how that applies. Okay. So K5 is another example of a non-planar graph. Let's do one more theorem. So if G is a planar graph, then G contains a vertex of degree at most 5. That is, this might be a little bit awkwardly stated, but think about it. This is saying that the minimum degree of G actually can't be larger than 5. So it's less than or equal to 5. Quick proof here. If G has n vertices q edges, if n is greater than or equal to 6, result is true, since it's not even possible to have degree more than 5 in that instance. So suppose n is greater than 6. Okay. If we let D be the sum of the degrees of each vertex all over the vertices of G, then whatever the sum is? We know from our very first theorem of graph theory, right? Day one of classes, that the sum over all of the degrees of vertices is equal to 2 times the number of edges. But Q, by this previous theorem, has to be less than or equal to 3n minus 6. So this is less than or equal to 2 times 3n minus 6, which is itself 6n minus 12. So D has to be less than or equal to 6n minus 12. We have assumed that the number of vertices is 6. If degree of each vertex was 6 or more, then D would be, this is the sum over all of the degrees of every vertex in G. G has n vertices. If the degree of each vertex was 6 or more, then D has to be at least 6n. 6 times the number of vertices. And the reason it's greater than or equal to is because I said 6 or more, right? So some vertices could have degree 8, 10, 25, whatever, right? But all of them have degree at least 6. So in this case, the smallest D could possibly be is 6 times the number of vertices. Okay? But D is less than or equal to 6n minus 12. So this is impossible. Because it cannot be less than or equal to 6n minus 12, simultaneously greater than or equal to 6n. So what was the problem here? It was assuming that the degree of each vertex was 6 or more. So there has to be at least one vertex that has degree no more than 5. Therefore, there exists at least one vertex with degree 5 or less. And that's all I wanted to say. Okay. Okay. To bring us to a place where we understand a little bit more about this Euler characteristic, it's necessary to, it's also interesting in its own right, but it's also necessary to introduce polyhedra. So next, I want to talk about regular polyhedra. I could, of course, just talk about polyhedra as well. The regular is not required here. But it's something that makes it easy. In fact, a polyhedron. What is it? So just a polyhedron is a solid bounded by flat surfaces. Let's take, of course, as an example, maybe you think of like this sort of thing, right? So this is a rectangular base prism. If all those rectangles are squares, the same square, this would be a cube. Okay, but maybe it's just a rectangular base prism. So I've drawn it here in a way to indicate that this is a three-dimensional object. Okay, here is an example of a polyhedron, or at least the surface of this thing is the polyhedron, right? Of course, it is actually a solid, but This is a polyhedron. This one, of course, the faces here are numbered. Okay, up to 20. It's a D20. If you know what this is, you know what the name of this particular polyhedron is, you can type it in chat. This is an icosahedron. So this is a 20-sided regular polyhedron. It's regular because it is made up of regular polygons for each of its faces. Each of its faces are equilateral triangles. Okay, so that's another example of polyhedron. Now, how does this relate to graphs? Well, if I put on the obvious vertices here for this thing, I can turn this into a graph in the following way. So there's a number of ways you can visualize this. I'm going to visualize it as basically I'm going to stretch the base out and then push the top down inside the base. So we're going to be looking straight down, like in this direction, if you like. If you think of me looking down from the top, of course, if this is a regular polyhedron, there's a lot of symmetry here, so what direction I'm looking at it on, it doesn't really matter. But let's just say here, this is the picture I'm looking at. I'm looking down. I'm going to stretch out the bottom and push the top down and then record the resulting edges. So here is like my base that I have maybe stretched out a little bit to accommodate. And here is like the inside. That's the top that's been pushed down inside this. But the thing is that I didn't disconnect any of the edges here. So for instance, here's the bottom. That's present here. Here's the top. That's present here. But this top vertex is also connected to this bottom vertex. And this one is connected to this bottom vertex. And similarly for the others. And so this is what I have. Question. What do you notice about this graph? So, what is true about this graph that I have come up with as a representation for this polyhedron? Well, it is planar. Can I do that for a polyhedron period? The answer is yes. So in fact, each polyhedron can be associated to a planar graph in this way. For a polyhedron, there is no reason to talk about bound degree and regions and that sort of thing, because here it's just obvious what's going on. So these points are the vertices. The one-dimensional objects connecting vertices are the edges. And these numbered surfaces, these numbered flat surfaces that form the actual exterior of the polyhedron, these are the regions themselves, right? These are the faces of the polyhedron. So you have vertices, edges, and faces. Okay, and that's why I substituted the word face when I was talking about regions earlier. So that is what's going on here. I'm saying that each of these are associated to a planar graph, which means that Euler's formula applies to them. So we have the following theorem. If a polyhedron has V vertices, E edges, and F faces, right, then that corresponds to a planar graph having V vertices, E edges, and F regions. Euler's formula applies, so this means that vertices minus edges plus faces is equal to 2. Okay. So this is the first thing. Okay. A quick aside. Quick question. What is it that's actually going on here? So this Euler's formula applied to graphs. It applied to planar graphs specifically, but a polyhedron can be associated to a planar graph. So that it applies to this for the same reason that it applies to planar graphs. But what is it that's actually what is happening here? So the answer is the quantity V minus E plus F is what is called the Euler characteristic of a right now I'm just going to say a two-dimensional object. You might complain and you might say, but a polyhedron's a three-dimensional object. Well, not really, right? Because while it may sit in 3 space, a polyhedron is two-dimensional for the same reason that the two-dimensional sphere is two-dimensional. So what does a two-dimensional sphere look like? It looks like this. Right? It's the model of the Earth, right? And hey, guess what? The surface of the Earth is two-dimensional. You know how it can prove it's two-dimensional? How many real numbers do you need to describe any position on it? 2, right? Latitude and longitude. If it was three-dimensional, you'd need 3. You might complain and say, well, there's altitude, right? There's a height. But we're talking about, idealizing this as it's the surface. So imagine you're some fixed distance, like above, out from the center of whatever you're calling the center. That's the center of our sphere. That's what it means to be a sphere. You're at some fixed distance there. So you are high enough that you can fly around the Earth without any obstruction, without hitting anything. The point is that you only need 2 numbers to describe where you are. You fix the height. You might say that's cheating a little bit, but no, this is really showing that it's truly a two-dimensional object. To see that it's truly a two-dimensional object, look at what we can do by representing a polyhedron in 2D on paper in this fashion, right? Is another way. But the easiest way is to just say, well, imagine a bug, right, that is restricted to the surface of a sphere. When we say a sphere, we're just talking about the surface. We're not talking about what's inside. That's another thing that confuses students sometimes. When I draw this, only the sphere, only the surface exists. What's inside it is hollow and does not exist. It's just not there. So, a bug or a person trapped on this, they have their feet glued to this surface. You only need two numbers to describe any coordinate where they are. Two numbers, latitude and longitude, describes exactly where they are on this thing, and that's why this is two-dimensional. So anyway, this quantity is the Euler characteristic of a two-dimensional object. The Euler characteristic, typically the letter we use is the Greek letter chi. To describe this, we are going to have a different meaning for this, so I'm not going to really use this. I'll always say Euler characteristic when I'm talking about this. This is called the Euler characteristic. This is an example of what is called, this is a topological invariant. This is what is called a homotopy invariant. Now, you don't have to know what those words mean, but this is the key. So invariant, of course, means it doesn't change with respect to something. So being a homotopy invariant means it does not change with respect to homotopy equivalence, which is an equivalence relation that exists between topological spaces, or that can exist between topological spaces. It's a topological invariant for the same reason. This is showing that it's a topological invariant. Well, what does this have to do with anything? So the actual truth. Every polyhedron, thus every planar graph, because this correspondence can be done in both directions. Okay. But every polyhedron, because we're looking at it, is homotopy equivalent to the two-dimensional sphere S2, which is this thing. So this is homotopy equivalent to the two-dimensional sphere. Homotopy equivalence you can think of as being, it is basically, you can think of it as being it's continuous deformations. So you're not allowed to break, but you can stretch and deform so long as you're not breaking. That's really the problem. So take this. Imagine this icosahedron was made up of like some kind of rubber, latex or something that could be inflated. Okay, and see how it has these edges, these sharp edges and points and stuff. Imagine I took this and I blew into it so that I inflated it a little bit, and I inflated it enough that it became like perfectly spherical. That inflation deformation on this would be a transformation, a homotopy equivalence between this and the sphere. So any kind of object like this, you can pick. There's other polyhedron you can pick. Pick your favorite. Here, let's see. Here, pick your favorite anime box set. Right here. This is again some like rectangular based prism. Even this can be deformed in a way to be this S2, this sphere. You will hear the joke frequently that topologists cannot tell the difference between their cup of coffee and a donut because, and if you look on the Wikipedia page for this, for topology, I'm sure they show this animation, because you can continuously morph a coffee mug into a donut, into the shape of a donut or a torus, and there's no problem with that. So those two things homotopically are equivalent. That might seem like there's way too many things that are equivalent like that. This is how topology rolls. This is just how topology goes. So anyway, every polyhedron is homotopy equivalent to the two-dimensional sphere. So that's one. Two, homotopy equivalent spaces have the same Euler characteristic. And three, the Euler characteristic of S2 is 2. So every polyhedron has Euler characteristic 2. But this Euler characteristic is this vertices minus edges plus faces for a two-dimensional object. You can define Euler characteristic for higher dimensional objects, and it keeps this alternating sum structure. I won't say too much more about it, but this is what's actually going on. The reason I wanted to show this is because actually the reason we passed to using the Euler characteristic in this way was the same reason the Euler characteristic was used in topology, which is figuring out when two spaces are homotopy equivalent is hard. This is a hard question to answer. Given two random spaces, I'm not going to give the definition of homotopy equivalence because it would take too long to define it. But basically, this is a very hard question. Two random spaces asked whether or not they're homotopy equivalent. Very, very hard to say. So because you would need to, if they're not homotopy equivalent, you would need to show that the certain function, the certain map you would need is impossible. It's a bit like showing that any representation you try for a planar graph like can't exist, right? There can't be a planar representation. So what is useful though is to come up with this invariant, the Euler characteristic, which has to be the same if they're homotopy equivalent, and then show that the Euler characteristic is different, right? Now, the invariant doesn't help you to construct the thing to show their equivalent if they have the same Euler characteristic. So this is one of those things that's kind of it's better for showing that things are not equivalent in a way than showing that they are, because the converse isn't true. Having the same Euler characteristic doesn't mean homotopy equivalent, but you have to assume some other things to get that. Slightly though, it's almost that good. But anyway, so the reason that this was introduced is actually the same reason that we used it, which is we need a better way of showing that something's non-planar, and this was the perfect thing. So back to this. Define for a polyhedron P rho of P, which is the minimum bound degree of one of these regions, one of these faces. Okay. The theorem is that for all polyhedra, this is between 3 and 5. I'm not going to do this proof. It's not that long, but it's actually just like a few paragraphs, a couple paragraphs on page 81. But yeah, for polyhedra, this number is very restricted. This actually is massively restrictive on what this could be. Like if you're trying to make a polyhedron with very, very many, or with faces that have like a lot of edges, well, it's not really so feasible, right? So this is part of what restricts the following, which is a regular polyhedron is a polyhedron whose faces consist of identical, congruent, regular polygons. What is a regular polygon? A regular polygon has all congruent sides and angles. So regular three-gons are equilateral triangles. Regular four-gons are squares. Right? You might say, well, what's wrong with a rhombus? So a rhombus doesn't have all equal angles, right? Square has all 90-degree angles. You know what a regular pentagon looks like. If I ask you to draw a pentagon in your head, you're thinking of a regular pentagon, not some generic pentagon, right? Regular hexagon, regular septagon, you might have an issue with. Regular octagon, you got no problem with. And so on in that fashion, right? Okay. Theorem. We won't say due to anybody. This was known even to Plato, and might have been known to the Pythagoreans. I'm not sure. That's possible. I'm not sure exactly from when this was known, but it was definitely known to Plato. So it's been known for a little over 2,000 years. There are only 5 regular polyhedron. Or maybe I should say polyhedra here. These are the Platonic solids. There is a funny graph theory proof of these. So I'm not going to. Should I? Yeah, okay. Why not? We'll do it. So let P be a regular polyhedron. Let G be its associated planar graph. It's guaranteed to be planar. Let V, E, F be as usual. The vertices, edges, and faces. The faces are the regions of P, or the regions of its associated planar graph. Since the faces of P are congruent, each is bordered by the same number of edges, say K. All faces are congruent. Each is bordered by the same number of edges, say k. The previous theorem that says for any polyhedron this minimum bound degree is between 3 and 5 says that k is between 3 and 5. And those are the options. Further, since the polyhedron P is regular, the graph G is also regular in the sense that each vertex has the same degree. This is why we actually use the word regular here. So we haven't mentioned regular graphs since some of the exercises. Homework 3 says it's due 22nd of July. Well, that's a mistake. It's due tomorrow. But what did I do here? Let's see. I'll have to fix that. What did the announcement say? That's the question. Did I at least get the announcement right? Yeah, let me have I'm looking at the announcement right now. The announcement got it right, but I guess in the actual file I left the statement from homework 1 or 2 or whatever, wherever I copied the top from. No, it's maybe when all of the on homework 3 and everything, maybe when I put it in Elms I put the wrong date. That's fine. I'll fix that. No one's gonna get points taken off because I said the homework was due on Elms a week before it was assigned or whatever, or 5 days before it was assigned. So yeah, you don't have to worry about that. Midterm will be at the end of this week. I'll post it like Friday evening, basically, and it'll be due next Monday. Okay. So, yeah, we haven't really mentioned regular graphs that much since like the first day of class, but regular just means each vertex has the same degree. So that is the case. So every vertex has the same degree. Call it R. We know that R is greater than or equal to 3. Okay, and so again, from this theorem, so what does this mean? If we're summing over all of the vertices, the total sum of degrees is going to be R, whatever this R is, times the number of vertices. That total sum, of course, by the first theorem of graph theory is 2 times the number of edges. Okay, and of course that has to be equal to k times the number of faces. This is the number of edges bordering each face. So this has to be true with this middle equality coming from the first theorem of graph theory. Okay. Well, let's think for a second. What do I know? Well, I know that so by our, maybe I'll give myself more room here before I run out of space. I know that 2 is equal to the number of vertices minus the number of edges plus the number of faces. Okay. I need more here to work with. So I'm going to do some algebraic trickery here. So I'm going to multiply both sides of this by 4. So this is going to be 8 is equal to 4v minus 4e plus 4f. Then I'm going to rewrite this ever so slightly as 4v minus 2e plus 4f minus 2e. So I split the minus 4e here as minus 2e minus 2e. I did that specifically to use this fact. So I'm now going to substitute for those copies of 2e's r times v and k times f. So this is going to be 4v minus rv plus 4f minus kf. So now this has a v in common, this has an f in common. So this is 8 is equal to v times 4 minus r, so 4 minus r times v, plus 4 minus k times f. So, of course, v and e are positive. I know that k is between 3 and 5. R is at least 3. So there's actually only a few cases that make this work. You might be asking yourself, how did the Greeks know this if they didn't use graph theory? There are many, many ways to prove that there are only 5 Platonic solids. You can even do this, you can have kids do this with like construction paper and trying to fit together regular polygons, because when you're trying to fit together these polygons, you'll notice that they have to be convex. They have to be convex and they have to close in order to form the polyhedron, right? So when you're trying to fit together the faces, the polygonal faces, there's a massive restriction placed on like the angle measurements, for instance, around each vertex, right? If the angle measurements aren't right, then you're going to end up with something that doesn't close, or it like lays flat, right? It like lays totally flat, so there's no polyhedron either. So there's many, many ways you can see this. Tons and tons of ways to do this. This is just a cute graph theory proof of this fact. So there are only a few cases here. There are only 5 cases. Case 1. What if r is equal to 3 and k is equal to 3? In this case, v is equal to f, so the number of vertices is equal to the number of faces. 8 is equal to v plus f, and v and f are both 4. V and f are 4. Number of vertices, number of faces is 4. This is what is called a tetrahedron. If you've ever played Dungeons and Dragons, this is a D4. Two. What if r is 3 and k is 4? Using this relationship, this implies there are 8 vertices and 3 times the number of vertices equals 4 times the number of faces, which implies that the number of faces is 6. This is a cube. Or if you play Dungeons and Dragons or other dice games that use a 6-sided die, this is a standard D6. Right. Similarly, in case 3, if r is 3 and k is 5, so here the number of edges bordering a face are 5, so the faces have to be pentagons. Okay, so in this case, 8 is v minus f. 3v is equal to 5f. If we solve this, this gives us that there are 20 vertices and 12 faces. This is a dodecahedron. Or a D12. If R is equal to 4 and K is equal to 3, then F is equal to 8. And you can find the other things, but once I know that there are 8 faces, this is an octahedron, or a D8. And lastly, case 5, R is equal to 5, K is equal to 3. You will see that 8 is minus V plus F, and 5V is equal to 3F. If you solve that system, you get that you have 12 vertices and 20 faces. This is an icosahedron, or a D20. Or this thing. Right? That's it. That's all the Platonic solids. Here's all the Platonic solids and the associated planar graphs. Look at the planar graph for the icosahedron. Right? I mean, the tetrahedron almost looks like its planar graph even. Right? Okay, so this is just a neat little way of proving this fact. It's been known for thousands of years using graph theory instead. Okay. Now, so far, we have only seen 2 non-planar graphs. Right? So we have only seen 2 non-planar graphs. K33 and K5. Question is, how many more are there? There's the answer here is basically K33 and K5 are the only obstruction, the only obstructions to planarity. We'll see what this means next time. Okay. So we will see what this means when we say these are the only obstructions. But basically it means that these are more or less the only ones that are actually causing us problems. And that might be a little bit shocking, might be a little bit surprising. We'll see that there's more graphs than just K through 3 and K5, but you'll understand what I mean by these are basically the only obstructions. It's basically if graphs don't somehow contain these, either as subgraphs or otherwise, we'll define what it means to be a subdivision next time, then they're planar, essentially. So that in that sense, these are basically the only obstructions. Okay, so that is that. I think that's pretty much all the time I have for today. So I'm going to stop here, and I will see you all tomorrow.